Stephen Strong. I'm an 84 alum, and the title of my talk today is What is the Opposite of a Quantum Computer? And as we all know, the word opposite is dangerous. I'm going to mean opposite in a very narrow sense of my own choosing. Not in the sense of it's a terrible way to get research funding. Quantum computers are a great way to get research funding. Now, for preparation, this is going to be what I call a modified type 4 talk. I've based my nomenclature of talks on Matt Groening's types of college TAs. So type 4 means that the talk should be loony, entertaining, scary, and it's dangerous because it may turn you into a believer. It's a modified type 4 talk because while I will be defying all expert opinion, I will only be defying some history. And I'll be logical in my own sense, but defying lots of other people's all logic. How about that? So, there you go. That is the opposite of a quantum computer. Thank you for coming to my TED Talk.
It's pretty.
More explication. Okay. So, what's a quantum computer? Very briefly, as opposed to a classical computer. So, in classical computation, we're used to formal binary logic programming things, right? Now, that probably exists as the limit where things are not zeros and ones, but more probabilistic. And I always recommend that anybody who can force themselves to do it read James, because it's a great book. It's worth it just to see what was in John Maynard Keynes' undergraduate thesis. But they prove that if you take certain generally accepted axioms for probabilistic reasoning, Bayesian logic is the only consistent probabilistic logic. So you're like, wow, are we done? Well, not quite. Because those are certain axioms, but you can modify the probabilities add axiom to do an amplitudes add axiom, a la quantum mechanics. And this can get you some funky expletive, because unlike probabilities, amplitudes can cancel. So the electron can get there by going right, the electron can get there by going left, but the electron can't get there at all. So because of this possibility for amplitudes to cancel, in this consistent quantum logic, which is a valid alternative to classical logic, computational universality classes can be completely different, and some problems that are unbelievably hard classically can be not so bad. Quantum sounds great. So why don't I have one? So let us journey back in time to the age of wooden children's toys and the iron Copenhagen interpretation of quantum mechanics. So in the 30s, when nobody knew any better, and we were like, how do we have these strange rules, and why didn't we have them for 5,000 years before now? I said, well, basically, big things, they're always getting measured by the environment. And measurement collapses the wave function, so you get classical physics. But tiny and isolated things avoid getting measured. They obey quantum physics. This, of course, has the problem of being a strict dichotomy. And you're like, well, what, am I A or I'm B? When does it happen? When do I cross over? So, for a long time, this was just kind of mystical stuff, and people smoked pot and wrote books about dancing woolly masters. But around the time I was in graduate school, more modern ideas took over. So neglecting fun things like Bohm's quantum potential and Everett's many worlds, decohering histories was the cool idea for resolving this in my day. So, and I think it still is. So Copenhagen, big coupled things are totally classical. Small, isolated things are totally quantum, and those two corners are nevers. Doesn't happen. So in decohering history, we say, okay, classical physics is a limit. Quantum rules are correct, they're always correct, but they can be very well approximated by classical laws in a certain context. So what's the context? So, Dirac here pointed out that if you looked at a path integral formulation of, a Lagrangian formulation of classical mechanics, turned it into a path integral version of quantum mechanics. Something like Huygens' principle gave you classical mechanics, and the idea is that these actions, you have exponentials of complex numbers, and if that complex number is order 10 to the 23, which is very big, but is also Avogadro's number, so it describes baseballs and us, then errors in numbers of order 10 to the 23 are always very large compared to 2 pi. And if it's in a complex exponential and you're off by some unknown thing gigantic compared to 2 pi, then you don't really have a phase. You can just treat it as though the phase were random for all practical purposes, and then you get basically that probabilities add and amplitudes can't cancel because they don't have meaningful phases. So the canonical paper in my day about understanding decoherent histories was, of course, called Dynamics of a Dissipative Two-State System. What says quantum coherence more than that title? So decoherent histories, you're like, well, now we can fudge it. Generically, classical, generically quantum. They actually specifically discussed whether or not you could make a Josephson junction that had quantum coherence despite being macroscopic. And nowadays we talk about, can I build something big and coupled enough to do a quantum computation and keep my coherence? So that would be a quantum computer. So now we get to my peculiar definition of opposite, which is this corner. Seems pretty opposite. Certainly the opposite corner. It's also the opposite in the sense of tons of funding and years of obscurity. Because I started trying to convince people that corner could be interesting 30 years ago. And I gave up 25 years ago. But I'm back for a command performance. So, can you really have something that's tiny and isolated and not quantum? No, it's not that interesting. But you could have something that people say is tiny and isolated, and that they'd be stunned if you argued with them about. So in particular, we mean it's not isolated, but everybody says it should have been isolated because of something called Landau's theory of the Fermi liquid. So we're going to look for a novel breakdown of Fermi liquid theory. So I'll give you the lightning, my version of what his Landau's Fermi liquid theory says. It's, well, you know, if I had non-interacting particles, they'd have quantum coherence. And if they were fermions, they'd fill up a Fermi sea to a Fermi surface. And then if they were very low energy excitations I was studying, they actually couldn't interact because of the phase space exclusion from the Pauli exclusion principle. And then I'd be back to having non-interacting quasiparticles. So this is a self-consistent argument. And the question is, though, is it an exhaustive argument? Can anything else happen? And the answer, of course, we already know is yes, other things can happen. But it's a very small list. Right? You essentially have the fractional quantum Hall effect. And then you have a bunch of things that are best thought of as fitting within Fermi liquid theory in ways that are relatively simple modifications, although, you know, at the time, superconductivity is a great mystery. And then, for idiosyncratic reasons of my own, I think Felix Bloch's contribution to this is widely neglected and super important. So, how do we get outside of this self-consistency? So we want to be outside of it, but we want to point it where we're going, and we want to give it a fair chance. We don't want to just be like, oh, you know, that's all crap. So, can electrons in a pure material at zero temperature not be asymptotically non-interacting? And that's where I would say it's fair to say all expert opinion is roughly no, except for fractional quantum Hall effect in a few cases. So we're going to talk about doing a Gedanken calculation where self-consistency fails. So we're not going to assume the higher D curved Fermi surface, but we will have one-dimensional stuff we understand, and then we're going to perturb in adding dimensionality. So imagine chains or planes, and you're coupling them to make a three-dimensional material. So if you find that that coupling is what technical term or normalization group relevant, all expert opinion says, well, now you give up, start with Fermi liquid theory again. And I'm like, no, I'm not give up. I want an interesting answer in the other corner of the phase diagram. I'm claiming there's a hidden assumption here that just because that coupling is relevant, it's also coherent. So we take an analog from this RevMod Phys paper, where we take two Luttinger liquids, technical term, we start them in their isolated ground states, we start them with different particle numbers, and we turn on the ability to move from flavor 1 to flavor 2, and quantum coherence is supposed to mean that it does this. There were more of these, more of those, more of these, more of those, but you could just get slow relaxation. Oh boy, there's no way I'm finishing in time. So, is arguing that you don't get slow relaxation enough to really claim you're sort of type 4, everyone else is wrong about this? Well, you know, probably not, except we have, boy, this is a real rush, this beautiful experiment. And the thing about this experiment is it's a magno-resistance experiment where the magnetic field is a direct probe of what happens when you vary phases. And varying phases can only matter if you have quantum coherence. So the claim is that in this very complicated diagram, there's only one magnetic field direction that can matter because there's only one sense in which you haven't lost coherence. And so this is the data replotted versus one thing, which is the only thing that's allowed to matter. And you see they collapse beautifully onto one thing. And so we have that, and then we also have this. And this is great because we're doing the same thing, but now the magnetic field is in the same direction as the transport, where under basically any sensible theory it doesn't do anything. And instead it's the only thing that does something. And once again, it lies on a beautiful line. And then I'll go just briefly over, because of the beautiful irony of this plot here, which looks nothing like that. It looks nothing like it because it's not supposed to look anything like it, because it's supposed to be in the regime where we think the Fermi liquid description is valid. But what's fun is this experiment had never been done until I demanded they do it. And the reason why it had never been done is because it was too easy. Because I was like, look, you know, this thing should be a Fermi liquid if we just actually have a weak enough magnetic field and a high enough temperature. And of course, you needed really good crystals, and by the time they were growing really good crystals, you stuck them in a 20 Tesla magnet, and you cooled down to like millikelvin. And I was like, but I want you to measure it like 2 Kelvin in like a 0.1 Tesla field. And they're like, that's too easy. I can't publish that. So I'm like, it's never been done? He's like, no. And I'm like, well, this is what's supposed to happen. It's supposed to look like a cosine curve there. And they said, all right, well, I guess if you have a testable theoretical prediction, I'll do the easiest experiment in the world. And so they did, and we were right. And we said, yay. And then everybody ignored the theory. And I yelled at people for 5 years, and then I quit and did other things with my life. And it's either wrong or brilliant, because 25 years later, it has 0 acceptance or mind share. So. Which takes us back to why it's a type 4 talk.